Hello everyone, today we are going to talk about divisibility. Divisibility is one of the main notions in number theory. In this lecture, we will learn the basic properties as well as some standard techniques by using divisibility. So first, let's let z be the set of integers like 0, positive or negative 1, positive or negative 2, and so on. As we all know that if we take any integers a or b, they are from set z. However, what about a over b or b over a? These two numbers are not necessarily integers. But if we denote b as a times an integer c, then the b over a is definitely an integer because that equals c. We denote b over a as a divides b. This means that b is a multiple of a, and a is a divisor of b. A divides b. So now let's see some common propositions of divisibility. Propositions. The first proposition is that a divides a if a does not equals to 0. The second one is if a divides b and b divides c, then a divides c. Third, if a divides b and b does not equals to 0, then the absolute number of a is less than or equal to absolute number of b. Fourth, if a divides b and b divides a, then the absolute number of a equals the absolute number of b. Fifth, if a divides b and c divides d, then ac divides bd. Six, if a divides bi and I is bigger than or equal to 1 or less than or equal to n, then a divides c1 b1 plus c2 b2 plus c3 b3 and so on. c1 c2 can be any numbers. Seven, if a divides b and a divides b plus or minus c, then a divides c. So these 7 propositions are the common propositions of divisibility. So now let's try to prove them. Okay, the first proof is pretty easy because a equals a times 1. So a divides a times 1. For the second one, let's say that b equals a times c1 and c equals b times c2, and you can substitute b as a times c1 times c2, so a divides a times c1 times c2. For the third one, let's let b equals a times c, and obviously c does not equals to 0. So the a absolute of a is less than or equal to absolute number of a times absolute number of c. For the fourth one, if a divides b, then the absolute number of a is less than or equal to absolute number of b, as we learned in proposition 3. But if b divides a, then the absolute number of b is less than or equal to absolute number of a. So as this all possible, that means the absolute number of a equals absolute number of b. For the fifth one, that b equals a times c. Let's say a times c1, and d equals c times c2. So bd equals a times c times c1 times c2. So ac divides by bd. AC divides bd. For number 6, let's let b1 equals a times d1. So then we can translate c1 b1 plus c2 b2 all the way to the cn bn to the a times c1 times d1 plus a times c1 c2 d2 all the way to a times cn dn. So a divides this number. For number 7, we use the same method that b equals a times c1 and b plus or minus c equals a times c2. So we can substitute this into b. So a times c1 plus or minus c equals a times c2, and c is thus equals to plus or minus a times c2 minus c1. Therefore, a divides c. Now let's look at questions. So the first question is prove that a minus b divides a to the k minus b to the k for any k where k is a natural number and a minus b does not equal to 0. Proof. So there is a common formula for a to the k minus b to the k. Maybe we did not learn that in high school algebra, but we will learn that during university. So a to the k minus b to the k equals a minus b times a to the k minus 1 plus a to the k minus 2 times b all the way plus a times b to the k minus 2 plus b to the k minus 1. That is true for all k of natural number. If we know this formula, then it is easy to conclude that a minus b divides a to the k minus b to the k because a minus b divides a minus b. That's the first question. So now let's look at the second question. Prove that n squared plus 2n plus 2 divides n to the fourth plus 4 for any integer n. Proof. First, you can simplify n to the fourth plus 4, as we can see that it's kind of like a symbol of a squared plus b squared, where a equals n squared and b equals 2. So n to the fourth plus 4 plus 4n squared minus 4n squared. Because we all know that a plus b squared equals a squared plus b squared plus 2ab. So we plus 2ab here. And that can simplify as n squared plus 2 squared minus 4n squared. This, you can see that it is a form of a squared minus b squared, where it equals a plus b times a minus b. Thus, we can also simplify this as n squared plus 2 minus 2n times n squared plus 2 plus 2n. Thus, we easily solve the question. For the next question, prove if a minus c divides ad plus cd, then a minus c divides ad plus bc. So we try to find these two equations have any properties with a minus c. Proof. You can try to subtract them, as this is a subtraction. AD plus CD minus AD plus BC. That equals to AD minus AD plus CD minus BC. We can simplify this as, that's AB. Simplify this as A times B minus D, and this is plus C D minus B, and B minus D is a negative of D minus B, so A times B minus D, that equals to minus C times B minus D, and that equals to A minus C times B minus D. Thus, A minus C divides the first equation minus the second equation. So, as recalled from the properties, if A divides B and A divides B plus or minus C, then A divides C. In this case, B equals to AD plus CD, the first equation, and C equals to AD plus BC, which is the second equation. So A divides C, as we proved that. Now let's look at the next question. Prove first 255 divides 2 to the 2016 minus 1. Second, 15 divides 2 to the infinite number of 2 on the exponent minus 1, where the number of 2's right here is bigger or equal to 3, the times of 2. Proof. First, you can see that 255 is 2 to the 8th, which is 256 minus 1. So 255, you can change this number to 2 to the 8th minus 1. And as we recalled earlier, that A minus B divides A to the n minus B to the n, and we have proved this. And now we can make 2 to the A as A and 1 as B, So, and obviously 8 divides 2016. Thus, 2 to the 8th minus 1 divides 2 to the 2016 minus 1, and that's 255. And we solved this question. For the next one, we can use the same method, as 15 equals to 2 to the 4th minus 1, and we can take 2 of these 2's to here as 2 to the 4th, and to the infinity number of 2 on the exponent. Thus, A is equal to 2 to the 4th and B equals to 1. That's the same like the first question. So 2 to the 4th minus 1 divides by 2 to the 4th to the infinite number of 2 minus 1 to the infinite number of 2. So this solves the question.